Chemical Kinetics Part 14. Activation energy, symbolized with E subscript A, and energy profile or reaction profile diagrams. Activation energy is a concept that was first introduced in 1888 by a Swedish chemist with the name of Svante Arrhenius, one of the coolest names in chemistry. Let's consider that when reactants form products, they don't necessarily instantaneously turn from reactants into products. Here we have a reactant. This is called methyl isonitrile. We have a methyl group. Organic chemists would call that hydrocarbon group here a methyl group, bonded with the carbon to the nitrogen, and then that nitrogen is triple bonded to another carbon. Now in this reaction, methyl isonitrile will turn into acetonitrile, and what happens is this part of the molecule flips over. So now we have that methyl group, that same methyl group we had here, but now the carbon is bonded to a carbon and triple bonded to a nitrogen. So this end of the molecule just flips over. We could say that when this happens, between here and here, there is a transition state where the CN bond would be broken and the molecule would be in the process of flipping this end of it over before products were formed. So we can call this thing here, it's not really a molecule, it's the transition state between the reactants and the products, or sometimes it's referred to as the activated complex. This thing would have to be there at some point in time. In other words, the change from here to here wouldn't be just instantaneous. It would take some time. So let's consider an energy profile, or sometimes this is called a reaction profile diagram. Some people would call this a potential energy diagram because we're graphing out chemical potential energy for the chemicals on the y-axis versus reaction progress, in other words, the time that it takes for the reaction to progress, on the x-axis. So we'll start with reactants and progress through to products. Now the chemical potential energy of the reactants, and again this is methyl isonitrile, have to get some energy introduced to them. And what that energy will do is it will cause this CN bond to bend and stretch and eventually break. And when that happens, we'll be at the top of this diagram. That's called the transition state or the activated complex. Now once we get to that part, the reaction will begin to progress on its own and release energy as this carbon-carbon bond forms, turning into product. The activation energy is the energy needed to get to the top of this diagram, to the top of that peak. Now notice that if I draw this dashed line representing the energy of the reactants, the energy of the products, this is the acetonitrile here, is smaller. The chemical potential energy is smaller. It's decreased compared to the reactants. So we can say that the change in energy in this reaction is negative. Well, that means that this is an exothermic reaction. We'll take a look at an endothermic reaction in a little bit. The activation energy is the minimum energy needed to run the reaction. It's always the height from where the reactant potential energy is to the top of that peak. And we can say that the lower the activation energy, the faster the reaction occurs. So if that peak were lower, the reaction would happen more quickly. Remember that the change in chemical potential energy, whenever it's negative, means we have an exothermic reaction. And that the change in chemical potential energy when it's positive, well, that would mean the reactants would be lower than where the products ended up, right? We'd have to move up here, so we'd end up here somewhere. That would be an endothermic reaction. And also note that when we reverse the reaction, if we went from products to reactants, this endothermic process would be exothermic, right? We'd have to increase, or we'd have to have a positive delta E there for a change in chemical potential energy. So we would have to reverse the sign of the delta E if we went in reverse. And that's true for all reactions. Going in reverse would change the sign of the delta E. So let's take a look at that. Here we have reactants forming products. If we go in this direction, the activation energy of the forward reaction would be that amount of energy. And let's say this is an endothermic reaction moving forward. In other words, we end up with more energy for the products than what we started with for the reactants. So we would have to overall put energy into the chemicals. Now let's say that we start here and move backwards. The activation energy for the reverse reaction would be this amount of energy. And as the reaction progresses and turns into these chemicals, we would see that the delta E would be negative. It would be endothermic. All right, so then let's consider as well that sometimes we have reactions with multiple steps. There are multiple transition states. So here's a diagram where we have multiple transition states. We start with our initial reactants, and the first activation energy is the energy between those reactants and the height of that first peak. Remember, that's the transition state or the activated complex when we're there. Now that's not really a molecule, but that's the transition for when some of the bonds of the reactants are being broken. Let's say that this reaction has an intermediate. It does form a molecule, but this molecule itself continues to react. So some of the bonds from this molecule get broken as the reaction progresses again. Now we'd have a second activation energy between what's called this intermediate and this second transition state. And let's say that it forms another intermediate chemical. So the intermediate that forms here continues to react, and some of its bonds, the bonds in this molecule, get broken, and we get another transition state. Again, transition states are not molecules. They're molecules that have some bonds that are broken as the activation energy is introduced into the previous chemical. Now, after this third transition state, energy would be released, according to this diagram, and we would end up with our final products. And we could say that the total change in chemical potential energy would be from the reactants to the products, this amount of delta E. Now, because that's positive, this would be an endothermic reaction moving forward. So reactants and products, as well as any intermediates, would be molecules. Intermediates would be molecules that would be formed and reacted away. Transition states, also known as activated complexes, are not molecules. They're molecules that have some bonds that were broken and that will reform as another molecule, whether it's an intermediate or a product, get formed. So it's the state that where the one molecule is transitioning into another, where some of the bonds are broken. That's a transition state.